Hello everyone, this is Professor Robert Solis. Welcome to this next video lesson. What I'm going to do is to show you how to use the rules of Boolean algebra to reduce this circuit. Now, back over here we talked about these various rules of Boolean algebra. I also talked about De Morgan's theorems, and we're going to use that to reduce this circuit if it's even reducible. So the first thing that we're going to do is to write down what the signal looks like after each one of these different gates. So for example, A over at this location becomes A naught. Now if I have an input to an AND gate of A naught and B, then ANDing means that we're going to have A naught B as the output of this AND gate. Now we have an OR gate over here. It looks like the input is C, the other input is A naught B, so that means that over here we're going to have A naught, again this is an OR gate, so we say OR, and then C is the next input. Let's take a look at this guy over here. So there's a junction right here, or a connection right here. There's also a connection right here. So it looks like this is going to be B, and this right here is going to be C. So if I were to OR those, that would be B or C. This is the input into this NAND gate. This is the other input into the NAND gate. So what would happen is I would get the AND of this and the AND of this, and then I'm going to NOT everything. All right, so that would be A, B, or I should say A naught B, ORed with C, and that's going to be ANDed. So I'll just put parens over here, and that's going to be ANDed with B or C, which is the other input. Now, this right here is the inversion of the output, so that means that this output is going to be knotted. Okay, so that is the ultimate output of this circuit. Now the question is, can this thing be reduced? So what I'm going to do is I'm going to use these rules of Boolean algebra to see if we can reduce this circuit. Well, first of all, the first thing that I see in this case is that I have this NOT that applies to both this and this. I think that that's an excellent way to illustrate how we can use De Morgan's theorems. It looks like there's an overall NOT over the A and B, so that means that we could split them up. We'll have the NOT of A and the NOT of B, especially with the OR gate in the middle. Actually, no, I'm wrong. It looks like these two are ANDed, so we'll use the other De Morgan theorem. This guy over here, the NOT of quantity A and B can be broken up, so that's the NOT of A ORed with the NOT of B. So that means we're going to do something like this. Let me get my pencil. All right, so we're going to have A NOT B or C. We'll NOT that entire thing. Instead of the AND, that's going to turn into an OR, and then we'll have the NOT of quantity B or C, the NOT of that. Okay, so that takes care of this first part. Now, I think I can do something similar over here to get rid of this overall NOT over here. I think I'll just simply use the De Morgan theorem again, and it looks like if I have two things that are ORed together, that's the same thing as NOTing A and turning that OR gate into an AND, and then NOTing B. So that means that we'll do this. For this part over here, again, let me have my pencil. So I have this part, A, the NOT of A, B, and I'm going to take that overall NOT and just apply it to this one part over here. I'm going to change that OR into an AND operation, and then I have C, NOT by itself. All right, this section over here, I can do the same thing. I can just simply say that's going to be ORed with, okay, so I'll take this NOT over everything, the B or C, and I'll implement this De Morgan's rule, the first one. So that means that this is going to turn into B naught and C naught. Okay, it looks like I can still reduce the circuit over here. This is another operation using De Morgan's rules. This guy over here, the AND of quantity AB is the same thing as the NOT. I said the AND, sorry, the NOT of AB is the same thing as the NOT of A or the NOT of B. So let's go ahead and take care of this section over here. So that's going to be A. Here's the first NOT, and then that NOT is going to apply over here. So that's a NOT. Instead of AND, I'll say OR, and then I'll have B naught. Now that whole thing is ANDed with C naught. And then I'm going to OR that with B naught, C naught. Okay? All right. This can be further reduced because what happens is that not really just changes that into an A. So this is the same thing as A or B naught quantity times C naught. And that's going to be ORed with B naught, C naught. All right, so what I'll do is I'll just apply the AND operation with the C naught and the A. And so what will end up happening is I'll have A, C naught, ORed with B naught, C naught. Oops, let me rewrite that. That's pretty sloppy here. C naught. And that's going to be ORed with B naught, C naught. All right. So now we're starting to see more of a reduction of our circuit. Let's see if I can notice a property over here. It looks like B naught, C naught, ORed with B naught, C naught. Well, that's really the same thing as this rule over here. A or A is really the same thing as A. So in other words, this is really the same thing as A, C naught, ORed with, and since these two are the same, that's just simply the same thing as saying B naught, C naught. So it looks like this entire circuit can be reduced to something like this. All right, so let me go ahead and redraw that circuit to give you a demonstration of what that looks like. All right, so let me go into my library of gates here, and it looks like I am going to AND A and C naught. So I'll take this AND gate over here, move it over here like this. Oh, it's not snapping here. Oh, that's okay. I'll just put it like that. And apply A, C naught. Okay, so that first signal over here is going to be A. This is going to be C naught. And I'm going to OR that with the AND of B naught, C naught. So let me go ahead and bring in another AND gate. This guy over here. And that looks okay right there. One of the inputs is going to be B naught. And then it looks like the other input is going to be C naught. Now, if I wanted to, I could put inverters over here. So let's go ahead and do this. I'll put an inverter right here. And that is going to be connected to this right here. And if that's C naught, then that means that this would have to be C. And I'm also going to do the same thing over here with B. So again, I'll just put another inverter, something like that. And I'll draw a connection from here to here. And so that means that that's got to be B, because the inversion of B is B naught. The inversion of C is C naught. And over here, according to this equation here, I'm supposed to have B naught, C naught. So what I'll do is I'll just simply take this guy over here. I'll draw a dot like this. And I'll just simply draw this straight down and connect it right here. So that's really C naught that's being inserted over here. Over here, I have an AND gate that's going to AND A and C naught, which is the same thing as this over here. The output of this is going to be B naught and C naught. Lastly, I have to OR these two together, so I'll just take this guy over here, and that's the same thing as bringing the input over here and bringing the input over here. And I should say OR this operation and this operation over here, so that means that I would end up with A, C naught, ORed with B naught, C naught. So this is a much simpler way of looking at the circuit analysis as opposed to this, which can be a little bit more complex. The output of this is exactly the same as the output of this, and vice versa. So at that point, you'd have to make a determination as an engineer or a computer scientist, okay, which circuit are we going to go with, which output are we going to go with. You'd probably want to go with something like this because it's much easier to deal with. Okay? All right, so this is one example. I got two more for you. This is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.